Hello dear student, I am Islam. Today in this video we are going to discuss an important question of TFR 22, TFR PhD 2022. Okay, on this question from real analysis. Okay, so let's start. Okay, so here's a question. USB a real root function. USB it is given that USB a real root constant function on 0 1. Okay, this means U is a mapping from close 0 1 to R. Okay, and it's constant function means U is a constant function from close 0 1 to R. Okay, and it's given that Ux is non-negative means Ux greater than 0 for all x belongs to 0 1. Okay, and it's also given that U of value of U at half equal to 1. Okay, this condition given, and one more condition also given that this Ux less than 0 to x utility for x belongs to close 0 1. Okay, this is also given, and it is given that Ux less than value of Ux at less than 0 to x ut dt. Okay, it is true for x belongs to close 0 1. Okay, now and asking what is the value of e1, asking the question is what is the value of e1. Okay, so say Ux less than close 0 to x utility, it implies from here you can write Ux less minus 0 to x utility, this should be less than equal to 0. Okay, from here you can write easily for x belongs to close 0 1. Okay, so name it 1. Now I am considering a function. Let gx equal to, I am considering a function gx. Okay, gx equal to e to power minus x 0 to x ut dt. I am considering this function 0 to x equal to gx equal to e to power minus x 0 to x ut dt. Okay, where x belongs to obviously close 0 1 is the domain. Okay, now you can say easily since ut it is given continuous. Okay, it is given continuous on close 0 1. So this function 0 to x utility is differentiable. Okay, from Riemann integral, we know from Riemann integral if ut is continuous, then 0 to x utility this function will be differentiable. Okay, this function will be differentiable on close 0 1. Now we all know iter function is smooth function. It is differentiable on everywhere on R, so it differentiable on close 0 1 also. Okay, so it's the product of two differential function, so it function g will be differentiable. So this function g will be differentiable on close 0 1. Okay, you can easily say. So from here you can say that g is differentiable. This function g will be differentiable. G will be differentiable at on close 0 1. Okay, now what is the differential of this function? You can, if you going to compute GSS, then derivative will be e to minus x, and you have to apply ddx of 0 to x ut dt. Okay, and then it is stop 0 to x in 0 to x ut 0 to x ut it will stop, and derivative of e to minus x. Derivative of e to minus x with respect to x would be e to minus x and minus 1. Okay, so if you take out the common e to minus x, because here e to minus is present, also e to minus is also present in second term. Okay, so if you take out the common e to minus x, you take out the common e to minus x from both side, from left and right, from two term, first term and second term both have e to minus x. So take out the common e to minus x, so this gives an derivative of this function. What is the derivative of this function? If you apply the Leibniz rule, okay, derivative function 0 to x e to x, you have to apply Leibniz rule. The differentiation of 0 to x ut dt. For this you have to apply Leibniz rule. Leibniz rule given 0 to x, you have to partial difference del x of ut, okay, dt, and you have to differentiate this with respect to x, and you have to place in place of t the upper limit, so it will be ux, and lower limit difference will be 0, so it will be 0. Okay, I have done by Leibniz rule. It is done by Leibniz rule. Okay, by Leibniz Leibniz rule, and Leibniz rule is done by Leibniz rule. Differentiation under the integral sign is a differentiation under the integral sign. Okay, so it is function of t, so derivative of x will be 0, partial derivative of x will give 0, so this term will be 0, dx x will be 1, so this is ux, and this is minus 0, so this is ux. So differentiation of 0 to x utility will be ux itself, it will be ux, so it will be ux. You take out the common, so in bracket you will have 2ux, and there is minus, so it is minus outside, and 0 to x ut dt. Okay, so what is g dash x? So this is g dash x, this will be g dash x. Okay, so write clearly g dash x. So what is g dash x? G dash, therefore g dash x will be e to the power minus x, okay, ux minus 0 to x ut dt. Okay, and this is true for all x belongs to closed 0. Okay, now this we know e to power x function is increasing function. Okay, this function is increasing, it's positive function. We all know e to power x, we all know, since e to power x is positive for all x belongs to R. Okay, range of e to power x function is close 0. This function range is open 0 infinity, so it is always value positive. Okay, so you can say from here e to power minus x will be also positive for x belongs to R, so this is a positive function. Okay, and from 1 we have, see, from 1 we have ux minus 0 to x utility, this will be less equal to 0. Okay, ux minus 0 to x utility, this will be less equal to 0 from 1, so this is positive, this is positive, this is positive, and this will be negative, less equal to 0, so total will be less equal to 0. Okay, so g dash x will be less equal to 0 for x belongs to closed 1. So from here you can say, g dash x will be less equal to 0 for x belongs to closed 1. Okay, so I am writing that. So from here you get g dash x will be less equal to 0 for x belongs to closed 0, 1. Okay, hope it will be clear. Okay, now g dash x less equal to 0 for x belongs to closed 0, and also g is a difference function, so it will imply g is monotonically decreasing, g is monotonically decreasing. Okay, g is monotonically decreasing function, g is monotonically decreasing, or you can say md in short form, is monotonically decreasing on close 0, 1. Okay, now g is monotonically decreasing on close 0, 1. Okay, we get this, g is monotonically decreasing on close 0, 1. So can you say what happened then for all x belongs to close 0, 1? You can say for x belongs to close 0, x belongs to close 0 means 0 less than x less than equal to 1. Okay, less than equal to 1. Okay. So x belongs to close 0, 1, since g is decreasing function, means you can say x is 0 and 1, and g is decreasing function, g is decreasing like this, decreasing function. So value at g is graph of g. Suppose it is a graph of g. So since g is decreasing function, the value of at g at 0 will be must be greater equal to value of, suppose x here. So value of g at x. Okay. For decreasing function it will be true. Since x g is decreasing function, so value of at g at 0 will be must be greater equal to value of g at x. G at x. Okay. Will be greater than equal to sign volt. So you can say since x greater to 0, since g is decreasing, moderate decreasing, so you will have g0 will be greater than equal to gx. Okay, now what is g0? G0 I have defined in the function g that g equal to e to the minus x 0 to x equal to. Okay, from here you can say g0 gives e to the 0, e to the 0 means 1, and 0 to 0 and 0 to 0 this interval gives 0, so g0 is 0. Okay, see, I have taken gx equal to e to the minus x and 0 to x utility. Okay, so this is true for a belongs to closed zeron. So I can put in place of x, I can put 0. Okay, so if I put 0, so this gives e to the minus 0, and this integral from 0 to 0 you treat it. So integral from 0 to 0 is nothing but 0, close integral, and 1 into 0, so 0, so g0 will be 0, so value of g0 will be 0. Okay, so I get g0 greater than gx for x is close zeron. If g is monotonically decreasing, it will happen because g is strictly monotonically decreasing. For this case it will happen. Okay, now g0 is 0, so we get gx less equal to 0 for all x belongs to close zeron. Okay, this will get, so we get what you have to get, so we get gx less equal to 0. Therefore we get, from here you can say we get gx less equal to 0 for x belongs to close zeron. Now put the value of gx. Now you can put the value of gx. What is gx? Gx is equal to e to the minus 0 to x utility. I have defined previously here. I have defined here. Gx equal to 0 to x is e to the minus 0 to x utility. Okay, so put the value of gx. Gx is e to the minus x 0 to x ut dt. Okay, this will be less equal to 0 for all x belongs to close zeron, you can say. Okay, now e to the minus function will be positive function. Okay, I have previously told you that e to the minus is always greater than 0 for any x belongs to R. So for any x belongs to close zeron, it will be positive. Okay, so you can divide this. You divide this on both sides, or you can multiply both the inequality by both sides by e to the x. You multiply this is 1, so it will be 0 to utility. And inequality remains same. You can multiply e to x in both sides of inequality, and the inequality remains same because e to x is positive for x belongs to 0. You can say it's positive, so inequality remains the same time. Inequality will be less type. Okay, it will not change. It will be same. So 0 to x utility will be less equal to 0. You can say for x belongs to close 0. Okay, now this you can name it to 0 to x utility. This will be less equal to 0 for x to close 0. Now see, we have previously we have ux greater than 0. It is given that ux greater than 0 for x to close 0. Okay, it is given ux greater than 0 for x to close 0. So what have, so till now we have done. Now we have ux real function. This value will be greater than 0. It is not a function, it is given, and it's also given ux less than 0 to x ut dt. Okay, this is given ux greater than non-negative function and ux less than 0 to x utility. This is a given condition, but I have proved that ux 0 to x utility less than equal to 0. I proved this by 2, so you can say this will be less than 0, and for which is true, it will be true for all x belongs to close 0. Okay, so you can say it will be true for all x belongs to close 0. Okay, so by it will be by 2. Okay, now from here you see 0 less than ux, again it will be less than, forget about this term, ux less than 0 less than ux less than equal to 0. Okay, this gives, so for all x belongs to close 0 1. So if 0 less than ux or ux less than equal to 0, so a less than b less than a. This together imply ux equal to 0. Okay, so this gives ux a be a 0 function for x belongs to close 0. Means ux be nothing but the, you can say ux the 0 function. Its range will be 0, single 0, or you can say identical 0. You can say u be the identically 0 function. Okay, on close 0. Okay, but so since u be the identical 0 function on close 0, you can say value of any x at that belongs to close 0 will be 0. So you can say value of u half, since half belongs to, you can say half belongs to close 0, right? Close 0, so value of u at half will be 0, because u is nothing but 0 function, because it all value is 0 for any x belongs to close 0. This gives 0, so u half will be 0, but we have u half, it is given u half equal to 1. It is given u half equal to 1. The question, it is given u half equal to 1. It is given in the question u half equal to 1. So according to the question, you have u is equal to u half equal to 0, or according to the question u half equal to 1. So if it true, suppose it is true, then we must have, from this you can say, from this from this you can say, from this you can say we must have 0 equal to 1. Okay, but this is a contradiction. 0 never be equal to 1, so this is a contradiction. Okay, so you can say you can say such a function u never exists. Okay, you can say the question is mentioned value, what is value of u1 if the given function is sufficient determine u to find u1, or it is interval, then answer box no function exists. Okay, so in this question the answer will be no such function u. Okay, there are no such function u satisfying the given condition. Okay, so answer will be no such function, no such function, no such function u. Okay, such no function u exists that satisfies the given condition. Okay, and hopefully the answer will be no such function. The official answer key will be no such function. Okay, so here domain is given close 0 1, you can extend this domain. Okay, the result I have tell you that us is not a function and us less than 0 to utility. If it's true, then us is identical to 0. It will true for any domain from close 0 comma infinity. I am extending this result. You can say this problem is completed. Okay, now you can extend this result. Suppose f be a function from close 0 to infinity to r function. It is quantum function. Okay, and it is non-negative. It is given, and moreover, if fx less than 0 to x ft dt. Okay, this is true. If a function from close 0 to infinity, we have quantum function, and if it is non-negative, and if it is less than 0 to x ft dt, this is true. Then if this condition is true, then the only function satisfies this condition. If it is non-negative, this function is first non-negative, and if it is less than 0 to x ft dt, this condition also. Then only function satisfying this condition will be the 0 function itself. Only function satisfying this condition will be 0 function itself. Or you can say fx is equal to 0. Okay, for s belongs to closed community. This is similar result of the similar quite similar to the given problem. Okay, that problem had to come. Okay, their interval is close 0 comma infinity, and above the interval in the exam in which we are given close is subset close 0 comma 1. Okay, is true for close 0 comma infinity, so it is also obviously true for close 0 comma 1. Okay, so you can prove this similarly as I proved above. Okay, you can have to construct this function like this. To first construct the function gx equal to e to power minus x 0 to x ft dt. You have to construct the function, and it is continuous, so it is differentiable. It is differentiable, so you can say this function is differentiable on close 0 comma infinity. Okay, so from if you differentiate the function gx equal to e to power minus x, and this gives fx minus 0 to x ft dt. Okay, and this will be again non-negative less than 0. Okay, again the given condition, because it was less than greater 0 and it will be less than 0, so it will be less than 0 for it to close 0 comma infinity. Okay, so from here you can say g in function is decreasing, monotonically decreasing. Okay, on close 0 comma infinity. So from here you can say g0 will be greater equal to gx for less belongs to close 0 comma infinity. Okay, now g0 is in this case also 0, so it will be gx less than e to power x 0 to x ft dt. Okay, so from here you can say, see e to x is non-negative, you can multiply both sides by 2x, so this gives 0 to x ft dt will be less equal to 0 for x belongs to close 0 comma infinity. Okay, now from here you can say that fx 0 less than fx also given less than 0 to x ft dt. Okay, but I prove it less equal to 0. From here I prove it less equal to 0 for x belongs to close 0 comma infinity. So from here you get fx equal to 0 function. So I proved, I've done. So I have done the proof. Okay, so hope you get the result. So I can say the result, if function for close 0 to infinity, we want the function r, and if it's non-negative function says from this condition is very vital. If it's like 0 to x ft, then the only function says by this condition will be and by 0 function. You can prove this by by taking this function. Okay, very simple proof. So hopefully this question solution you have to clear, and I will discuss more solution in upcoming videos. Okay, so please subscribe my channel and see my video regularly. Okay, I'll upload more solution of Nbhm, and after that I will upload more solution CSIRNET, and also I'll upload lecture videos. Okay, don't worry. So please subscribe my channel and follow my channel. So thanks for watching and thank you.